The Earth, when seen from space, appears complete, mapped, measured, and understood. Yet this image is an illusion. Beneath shifting clouds and across fractured continents lie places that defy ordinary perception. Landscapes so extreme, so geometrically precise or visually distorted that they seem detached from the rules that shape the rest of the planet. Vast salt deserts that mirror the sky with impossible clarity. Valleys carved into forms too symmetrical to feel natural. Mountains rising in isolation, cut off from time, weather, and even biological evolution. How does a surface as chaotic as Earth produce environments of such unnatural perfection? What forces, geological, chemical, climatic, can sculpt reality into something that appears artificial? And more importantly, why do so many of these places remain remote, difficult to reach, and largely untouched? These are not myths. They are measurable, documented, and scientifically explained. Yet even with explanation, they remain deeply unsettling because they challenge the boundary between what we recognize as natural and what feels impossible. This investigation is not about fantasy. It is about process, time, pressure, isolation. Across deserts, oceans, volcanic systems, and ancient rock formations, we trace the origins of 30 of the most surreal locations on Earth. Each one is a result of precise conditions, rare combinations of physics, chemistry, and time that together reshape the familiar into something entirely unexpected. What emerges is not just a collection of landscapes, but a deeper understanding of how extreme environments redefine the limits of reality itself. How impossible landscapes begin. Long before these landscapes appeared surreal, they were ordinary, embedded within a restless planet defined by motion beneath stillness. The Earth's surface is not fixed. It is divided into massive tectonic plates, each moving slowly, almost imperceptibly, across a semi-fluid mantle. Over millions of years, these movements generate pressure, fracture continents, and lift entire mountain ranges from ancient seabeds. What appears today as an isolated plateau or an unnatural valley is often the visible result of forces that began deep below the crust, forces that continue, even now, beyond human perception. But tectonics alone do not create the impossible. Climate intervenes, ice advances and retreats. Oceans expand, then withdraw. Wind reshapes exposed surfaces grain by grain. It's while water exploits microscopic weaknesses in rock, widening them over centuries into vast formations. These processes are not random. They follow physical laws with relentless consistency. Yet, under rare conditions, their outcomes appear almost deliberate. Consider the alignment required. A region must first be geologically active enough to create elevation or depression. Then it must experience long-term stability, millions of years without disruptive events, to allow erosion to refine rather than destroy. Add to this a precise climate pattern, where rainfall, temperature, and atmospheric conditions interact in a narrow range. Only then can nature begin to sculpt structures that appear intentional. Time becomes the defining variable. A single storm alters little. 1,000 years carve subtle change. But over tens of millions of years, a repetition transforms landscapes into forms that challenge intuition. Layers of sediment compress into stone, only to be exposed again and reshaped. Mineral deposits accumulate, crystallize, and spread across surfaces in patterns dictated by chemistry rather than design. In certain environments, this balance becomes extreme. Flatness reaches near mathematical precision. Colors emerge from chemical reactions invisible to the naked eye. Structures stand isolated as if placed rather than formed. These are not anomalies in the sense of breaking natural laws. They are the purest expressions of those laws under rare and sustained conditions. What makes these places feel impossible is not their origin, but their rarity. Across the planet, countless regions undergo tectonic shifts and erosion. Yet only a fraction evolve into landscapes that appear detached from natural randomness. The difference lies in continuity. The uninterrupted application of pressure, climate, and time without interference. To understand these environments is to shift perspective, from seeing nature as chaotic to recognizing it as precise, given enough time. And it is within this precision that the first of these impossible places begins to emerge, not as a sudden creation, but as the inevitable result of processes that never stopped. The illusion of flatness, mirrors of the Earth. At high altitude, where the atmosphere thins and the horizon stretches beyond ordinary perception, the Earth reveals one of its most disorienting transformations, perfect flatness. In southwest Bolivia lies Salar de Uyuni, the largest salt flat on the planet. Is spanning over 10,000 square kilometers and elevated more than 3,600 meters above sea level. It is not simply vast, it is extraordinarily uniform. Variations in elevation across its surface are measured in centimeters. From a geological perspective, such precision is rare. From a visual perspective, it is almost incomprehensible. This landscape was not always a desert of salt. It is the remnant of prehistoric lakes, vast bodies of water that once occupied the Andean plateau. As climatic conditions shifted thousands of years ago, these lakes gradually evaporated, leaving behind dense concentrations of salt and minerals. Over time, repeated cycles of flooding and evaporation compress these deposits into a hardened crust, forming a surface both stable and remarkably level. Yet the true transformation occurs during the rainy season, and a thin layer of water, often no more than a few centimeters deep, spreads across the salt crust. Under ordinary conditions, shallow water creates distortion. Here, it does the opposite. Because the surface beneath is so flat, the water distributes itself evenly, forming a continuous reflective plane. Light, encountering this surface, follows a predictable path. It reflects with minimal scattering. The result is a mirror on a planetary scale. Sky and ground merge into a single visual field. Clouds appear beneath the observer as clearly as they do above. The horizon, normally a fixed boundary, dissolves. Without visual reference points, depth perception collapses. Distance becomes ambiguous. A person standing a few meters away can appear suspended in space, disconnected from any surface. This phenomenon is not an illusion in the traditional sense. It is a precise optical outcome, governed by the physics of reflection and the geometry of an almost perfectly planar surface. Satellite agencies have even used this location to calibrate instruments, relying on its consistency as a natural reference. And yet standing within it produces a cognitive dissonance that science alone does not resolve. The human brain depends on irregularity, shadows, textures, gradients, to interpret space. Remove these, and perception begins to fail. What remains is a landscape that feels constructed rather than formed, artificial rather than natural. But nothing here is artificial. It is the outcome of water retreating, minerals settling, and time enforcing uniformity over chaos. A place where Earth, through entirely natural processes, it achieves a level of precision that challenges the limits of how reality is perceived. And in doing so, it creates not just a surface, but a question. How flat can the natural world become before it no longer feels real? Erosion as an architect. There is no intention in erosion, no design, no blueprint, no awareness of outcome. And yet, across certain regions of the Earth, erosion produces forms so structured, so deliberate in appearance, that they seem engineered rather than formed. This process begins with imbalance. Rock, despite its apparent solidity, is rarely uniform. Layers differ in density, composition, and resistance. Some are compact and durable, others brittle and easily fractured. When exposed to external forces, wind, water, ice, these differences become amplified. Erosion does not remove material evenly. It selects, gradually stripping away weaker layers while leaving stronger ones behind. Over time, this selective removal creates contrast. Wind carries fine particles across exposed surfaces, acting as a continuous abrasive force. In arid environments, where vegetation is absent and moisture is scarce, this process intensifies. Sand grains collide with rock at high velocity, smoothing some areas while cutting sharply into others. The result is not random damage, but patterned transformation. Edges sharpened, surfaces polished, voids expanded. Water operates differently, but with equal precision. Rainwater seeps into microscopic cracks, expanding them incrementally. In colder climates, this water freezes, increasing in volume and forcing the rock apart. This freeze-thaw cycle repeats thousands of times, fragmenting entire sections of terrain. Rivers, and guided by gravity, carve channels that deepen over millennia, isolating pillars, arches, and steep-walled canyons. What emerges is structure through subtraction. Columns of stone stand where surrounding material has been removed. Natural bridges form when erosion cuts through weaker sections beneath more resistant layers. Entire landscapes evolve into fields of vertical formations, each shaped by the same forces but never identical. The consistency lies not in uniformity, but in process. Time, again, is the governing factor. These formations do not appear within human timescales. They require stability, long periods without tectonic disruption, to allow erosion to refine rather than reset the landscape. Even minor environmental shifts can alter the rate or direction of change, and influencing the final outcome in ways that are subtle but cumulative. There is also a threshold effect. In early stages, erosion appears chaotic. Surfaces are irregular, transitions abrupt. But as material continues to be removed, patterns begin to emerge. Balance develops between opposing forces, abrasion and resistance, collapse and stability. It is within this balance that erosion begins to resemble design. What appears intentional is, in reality, the result of constraint. Physics limits how rock can fracture. Gravity dictates how material can fall. Fluid dynamics governs how water flows and where it exerts force. Within these constraints, only certain shapes can persist. Over millions of years, everything else is eliminated. But the result is a landscape refined to its most stable forms, structures that seem improbable, not because they defy natural law, but because they represent its most precise expression. Erosion does not create complexity. It reveals it, and in doing so, it transforms disorder into something that appears, almost unavoidably, like architecture. Isolated worlds, evolution in separation. Isolation in geological terms is not simply distance, it is disconnection. Across the Earth, there are regions where physical barriers, mountain walls, deep valleys, surrounding oceans, or sheer cliffs have restricted movement for millions of years. In these environments, separation becomes a controlling force, shaping not only the landscape, but the life that exists within it. When a system is cut off, it begins to diverge. And a species that enter these isolated zones, whether by chance migration, climatic shift, or geological change, find themselves removed from external competition. Over time, they adapt to highly specific conditions, limited resources, unusual terrain, and microclimates that differ sharply from surrounding regions. Without outside genetic influence, these adaptations accumulate, producing organisms that are distinct, sometimes entirely unique to that single location. This process is known as evolutionary isolation. But the transformation is not limited to biology. The landscapes themselves evolve differently when separated. Erosion may proceed at a slower or more uniform rate due to reduced environmental variability. Sediment may accumulate undisturbed. Volcanic or tectonic activity, if present, can reshape the area without interference from larger continental systems. The result is an environment that develops according to its own internal logic, rather than the broader patterns that govern connected regions. One of the most striking consequences of isolation is stability. In many accessible parts of the world, ecosystems and terrains are constantly altered by weather fluctuations, migrating species, and human activity. In contrast, isolated environments often remain unchanged for extended periods. This stability allows processes to reach extremes. Plants evolve specialized survival mechanisms. Geological formations persist long enough to become exaggerated versions of their original state. Yet isolation also introduces vulnerability. Because these systems are self-contained, they lack resilience against sudden change. And a shift in climate, the introduction of an external species, or minimal human interference can disrupt balances that took millions of years to establish. What appears timeless is, in fact, highly sensitive. There is also a perceptual effect. To an outside observer, isolated landscapes often feel detached from the rest of the planet. Their features, whether biological or geological, do not match familiar patterns. Colors may differ. Structures may appear out of place. The absence of transitional zones reinforces this impression. There is no gradual shift from the known to the unknown. Instead, there is a boundary, beyond which everything operates differently. These are not separate worlds, but they function as if they are. Isolation does not create impossibility. It creates divergence, pathways of development that unfold without external correction or influence. Over time, these pathways lead to outcomes that appear unusual, not because they break natural laws, but because they follow them in uninterrupted isolation. And in that uninterrupted process, the Earth reveals how different it can become when left alone. Volcanic extremes and chemical landscapes. Beneath the surface of the Earth, heat remains constant, an internal force inherited from planetary formation and sustained by radioactive decay. In most regions, this energy is contained. In others, it rises, fractures the crust, and emerges with transformative intensity. Volcanic systems are not isolated events. They are conduits, pathways through which material from deep within the planet reaches the surface. When this material is released, and it does more than reshape terrain, it alters the chemical identity of entire landscapes. Lava, once exposed, cools into rock, but its composition varies. Some flows are rich in silica, forming thick, slow-moving masses that solidify into steep formations. Others are more fluid, spreading across vast distances before cooling into smooth, expansive plains. Each variation determines not only the shape of the land, but its long-term stability and susceptibility to further change. Yet the most visually surreal transformations often occur after the eruption. As volcanic material interacts with the atmosphere, water, and existing minerals, chemical reactions begin to dominate. Gases released during eruptions: sulfur dioxide, carbon dioxide, hydrogen sulfide combine with moisture to produce acids. These acids alter surrounding rock, unbreaking it down and redepositing minerals in new configurations. Color emerges from chemistry. Iron oxidizes, producing deep reds and oranges. Sulfur crystallizes into intense yellows. Copper compounds introduce shades of green and blue. In certain environments, these reactions occur simultaneously. Creating landscapes layered with contrasting colors, patterns that appear artificial but are entirely dictated by elemental interactions. Temperature also plays a defining role. In geothermal regions, heat persists long after visible volcanic activity has ceased. Underground water is superheated, rising through fissures and emerging as hot springs, geysers, or steam vents. As this mineral-rich water reaches the surface, it deposits dissolved materials in thin layers. Over time, these deposits accumulate, forming terraces, pools, and crusts with precise, repeating structures. These formations are dynamic. They grow, shift, and degrade in response to changes in temperature, water flow, and chemical composition. A slight variation in heat can alter the rate of mineral deposition. A change in groundwater pathways can redirect entire systems. What appears stable is, in reality, continuously evolving. Despite this activity, many volcanic landscapes give the impression of permanence. Their colors remain vivid, their structures appear fixed. But this is a temporary balance, a moment within a longer cycle of accumulation and decay. Eventually, erosion will act upon these formations, breaking them down and redistributing their materials across new environments. What makes these places feel unreal is not only their appearance, but their origin. They are shaped not by external forces alone, but by processes that begin deep within the Earth, processes that operate beyond direct observation. The surface becomes a record of internal dynamics, translated into color, texture, and form. In volcanic landscapes, the boundary between geology and chemistry dissolves. What remains is a terrain defined by transformation, where heat, pressure, and reaction combine to produce environments that seem incompatible with the rest of the natural world. Yet are entirely consistent with the forces that created them. Water beyond expectation. Water is often perceived as predictable, a substance defined by clarity, fluidity, and uniform behavior. It flows downhill, freezes at known temperatures, evaporates under heat. Yet under certain conditions, water begins to behave in ways that challenge these assumptions, producing environments that appear inconsistent with its basic properties. These deviations begin with composition. Pure water is rare in natural systems. It carries dissolved minerals, salts, gases, and organic material. The concentration of these elements alters its physical behavior, changing density, freezing point, and interaction with surrounding substances. In extreme cases, these changes produce bodies of water that no longer behave as expected. High salinity is one of the most significant factors. In enclosed basins where evaporation exceeds inflow, salts accumulate over time. As concentration increases, water becomes denser. This density affects buoyancy, allowing objects, and even the human body, to float more easily. In some environments, the density difference between layers of water becomes so pronounced that they resist mixing, forming stable stratifications. Temperature introduces another layer of complexity. In geothermal regions, water can be heated from below while remaining exposed to cooler air above. This creates vertical gradients, where temperature changes rapidly with depth. In certain lakes and pools, this results in distinct thermal layers that remain separated due to differences in density. These layers can persist for long periods, creating environments where heat and chemistry vary dramatically within short distances. There are also systems where water appears static. In subterranean or isolated basins, limited circulation prevents the normal movement associated with rivers or open lakes. Without mixing, sediments settle undisturbed. Air and chemical gradients intensify. Oxygen may be absent in deeper layers, creating conditions unsuitable for most life forms. These environments develop slowly, shaped more by accumulation than by flow. Optical effects further complicate perception. The clarity or opacity of water depends on suspended particles and dissolved substances. In some locations, mineral content scatters light in ways that produce unusual colors. Deep blues, opaque whites, or even reflective surfaces. In others, the absence of particles creates extreme transparency, making depth difficult to judge. What appears shallow may extend far below, while reflective surfaces can obscure the boundary between water and air. These properties are not anomalies. They are outcomes of physical laws applied under uncommon conditions. Water responds precisely to changes in pressure, temperature, and composition. When these variables reach extremes, the results deviate from everyday experience. The familiar becomes uncertain. A liquid known for consistency reveals variability that is rarely observed on a human scale. What emerges is a redefinition of expectation. Water is not inherently uniform. It is responsive, shaped by its environment. Altered by what it contains, and capable of forming systems that appear contradictory to its basic nature. In these environments, it does not simply occupy space, it defines it, and in doing so, it transforms from a passive element into an active force. One that reshapes landscapes, alters perception, and challenges the assumption that even the most familiar substances behave in predictable ways. Human interaction and hidden modifications. Do not all landscapes that appear impossible are entirely untouched. Across the planet, there are environments where human presence has altered terrain so subtly or so long ago that the boundary between natural formation and deliberate modification becomes difficult to define. In these places, time obscures intention. What remains is a surface that appears organic, yet carries traces of design. Human interaction with extreme environments has historically been limited by accessibility. Remote plateaus, dense forests, arid deserts, and isolated islands restricted large-scale intervention. Yet small, sustained efforts, often driven by survival rather than expansion, have left lasting imprints. Terracing is one such example. On steep slopes, early societies reshaped land into stepped levels to control water flow and prevent soil erosion. With these structures, built incrementally, follow the natural contours of the terrain. Over time, vegetation integrates with the modified surface, softening edges and blending construction into the surrounding environment. From a distance, the result appears as a natural pattern, regular, repeating, but not immediately identifiable as artificial. There are also cases where materials themselves define the modification. Stone, when arranged without mortar, weathers at a rate similar to its surroundings. Structures built from local rock gradually adopt the same coloration, texture, and erosion patterns as adjacent formations. As centuries pass, distinctions blur. Walls become ridges. Pathways become channels. The original purpose of the construction becomes secondary to its integration into the landscape. Those subsurface alterations are even less visible. Ancient drainage systems, tunnels, and carved channels redirect water beneath the surface. These modifications influence erosion patterns above ground, guiding the formation of valleys or stabilizing slopes. To an observer, the terrain appears naturally shaped, yet its development has been subtly guided. In some environments, human absence is itself a factor. Abandoned settlements, once maintained and structured, begin to decay. Without upkeep, buildings collapse, materials scatter, and vegetation reclaims space. Over time, these remnants merge with the landscape, forming irregular patterns that no longer resemble their original configuration. The distinction between constructed and natural features becomes indistinct. perception of these places is influenced by expectation. When a landscape appears too ordered, too symmetrical or repetitive, the instinct is to attribute it to design. Yet nature is capable of producing similar patterns through physical processes. Conversely, human modifications that align with natural constraints can remain undetected. Perceived as part of the environment rather than an intervention. This overlap creates ambiguity. What appears untouched may have been shaped guided or stabilized by human activity long ago. What appears constructed may, in fact, be entirely natural. The difficulty lies not in identifying individual elements, but in recognizing their origin within a continuum of interaction. Human influence does not always dominate landscapes. In certain conditions, it recedes, absorbed into larger systems governed by geology and climate. What remains is not a clear boundary between natural and artificial, but a convergence. And within that convergence, some of the most surreal environments on Earth emerge, formed by nature, adjusted by humans, and ultimately shaped by time into something that belongs fully to neither. Optical illusions in nature. Perception is not a direct measurement of reality. It is an interpretation, constructed by the brain, using visual cues such as contrast, shadow, depth, and motion. When these cues are altered or removed, the accuracy of perception begins to decline. In certain environments, this decline becomes pronounced. Producing landscapes that appear distorted, inverted, or physically impossible. These effects are not rare, but they are highly dependent on conditions. Light, as it travels through the atmosphere, is influenced by temperature and density. When layers of air differ significantly in temperature, light bends, a process known as refraction. In deserts or overheated surfaces, this bending can create mirages, where distant objects appear displaced or inverted. The brain, interpreting light in straight lines, reconstructs these signals into images that do not correspond to physical reality. Reflection contributes another layer of complexity. Smooth surfaces, water, ice, or even fine mineral deposits can reflect light with high precision. When combined with uniform terrain, these reflections eliminate visual boundaries. The horizon becomes indistinct. Objects appear suspended or duplicated. Without shadows or reference points, scale becomes uncertain. A structure or person may seem larger, smaller, nearer, or farther than it actually is. See, color perception is also subject to distortion. Mineral composition and atmospheric conditions influence how light is absorbed and scattered. Certain wavelengths are reflected more strongly, producing intense or unusual colors. In environments rich in specific elements such as sulfur, iron, or copper, these effects can dominate the visual field. The result is a landscape where color no longer aligns with expectation, further disrupting spatial awareness. Topography plays a role as well. Gradual slopes, when viewed without clear reference points, can appear flat or even inverted. This effect is amplified in areas where the surrounding horizon is obscured by fog, haze, or uniform terrain. In such conditions, the brain struggles to establish orientation. movement across the landscape may feel inconsistent with visual input, creating a sense of instability. These illusions are not errors in the environment, they are limitations in interpretation. The human visual system evolved to operate within familiar ranges of contrast, scale, and lighting. When these parameters are exceeded, perception becomes unreliable. The environment remains unchanged. It is the observer's understanding that shifts. There is also a cumulative effect. When multiple distortions occur simultaneously, refraction, altering position, reflection removing boundaries, and color modifying depth cues, the result is a compounded illusion. Each factor reinforces the others, producing a landscape that appears fundamentally unreal. Yet every element remains governed by physical law. Light behaves predictably. Surfaces reflect according to angle and composition. When atmospheric conditions follow measurable patterns, the illusion arises not from deviation, but from precision, conditions aligning in a way that exposes the limitations of perception. In these environments, reality is not altered. It is revealed in a form that is difficult to interpret, and in that difficulty, the familiar world begins to appear. Impossible, fragility, and threat. The landscapes that appear most permanent are often the most vulnerable. Their scale suggests endurance, vast deserts, elevated plateaus, deeply carved valleys. But the conditions that created them are often highly specific and delicately balanced. These environments are not maintained by strength alone, but by stability. When that stability is disrupted, change accelerates. Climate is the primary factor. Many of these surreal landscapes depend on narrow environmental ranges, A salt flat requires a balance between evaporation and precipitation. Too much rainfall, and its reflective surface becomes irregular. Too little, and the processes that maintain its structure begin to decline. Similarly, geothermal systems rely on consistent heat flow and groundwater supply. Alter either, and the visible features, terraces, pools, mineral deposits begin to degrade. Temperature shifts introduce further instability. In cold regions, freeze-thaw cycles shape rock over long periods. As global temperatures rise, these cycles weaken or disappear, slowing the processes that maintain certain formations while accelerating others, such as permafrost thaw. This can lead to structural collapse, landscapes that took millennia to form, breaking down within decades. Human activity amplifies these effects. Even limited presence can alter fragile systems. Foot traffic compacts surfaces, disrupting natural patterns. Vehicles leave tracks that persist for years in environments where erosion is slow. In mineral-rich areas, extraction activities remove not only material, but the chemical balance required to sustain visible features. What appears as a small intervention can trigger cascading changes. Water systems are particularly sensitive. Diverting a river extracting groundwater or altering drainage patterns can reshape entire regions. Reduced water flow limits mineral deposition. Increased flow accelerates erosion. In closed systems, these changes are not easily absorbed. They accumulate, shifting the equilibrium of the landscape. There is also the issue of time compression. Natural processes operate across geological timescales. Human-induced changes occur rapidly by comparison. When a system adapted to slow variation encounters sudden disruption, it cannot adjust. The result is not gradual transformation, but abrupt degradation. Yet the impact is not always immediately visible. Some landscapes retain their appearance even as underlying processes fail. A geothermal pool may maintain its color while mineral deposition slows. A salt flat may appear intact, while structural consistency weakens beneath the surface. By the time visible changes occur, the system may already be in decline. These environments are not static monuments. They are active systems. Their forms represent a balance between competing forces: deposition and erosion, heat and cooling, accumulation and loss. Disturb that balance, and the defining characteristics begin to fade. What makes these places remarkable is also what makes them fragile. They exist because conditions aligned with precision. Maintaining them requires that this alignment continues. And as those conditions shift, through climate change, resource use, and increasing human reach, the question is no longer how these impossible places formed, but how long they can remain. The limits of understanding. Across these landscapes, a pattern begins to emerge, not in their appearance, but in what they reveal about the limits of interpretation. Each location examined, whether shaped by tectonic force, erosion, chemical reaction, or isolation, follows known physical laws. None exist outside the framework of geology, physics, or chemistry. Their formations can be measured, modeled, and to a degree predicted. And yet, when experienced directly, many of these places resist intuitive understanding. This tension defines their significance. Science provides explanation, but explanation does not always resolve perception. A salt flat can be described in terms of mineral deposition and surface uniformity, yet standing upon it produces a disorientation that those descriptions do not fully convey. A geothermal system can be reduced to heat transfer and chemical gradients, yet its colors and structures appear detached from expectation. What is understood analytically remains unfamiliar experientially. Part of this limitation lies in scale. Geological processes operate across timescales that exceed human reference. Millions of years compress into static images, rock formations, layered deposits, and vast plains, without visible indication of the duration required for their creation. The human mind, adapted to immediate cause and effect, struggles to reconcile such extended continuity with present observation. There is also the issue of abstraction. Scientific models simplify complexity. They isolate variables, define relationships, and produce frameworks that can be communicated and tested. But in doing so, they reduce environments to components. The full system, where multiple processes interact simultaneously, is more intricate than any single model can represent. These landscapes exist within that complexity. They are not the result of one force, but of many operating in parallel. Pressure from below, erosion from above, chemical transformation within, and environmental stability sustained over time. Each factor contributes, but none alone defines the outcome. Uncertainty remains an essential element. While much is known, gaps persist. Subsurface dynamics, long-term climate interactions, and the precise thresholds that produce certain formations are not always fully understood. In some cases, landscapes are documented before their processes are completely explained. Observation precedes comprehension. This does not diminish scientific understanding. It refines it. Each of these environments acts as a natural record, evidence of conditions, sequences, and interactions that extend beyond direct observation. By studying them, scientists reconstruct histories that would otherwise remain inaccessible. The landscapes become data, encoded in form and composition. Yet even as knowledge expands, perception continues to lag behind. What appears impossible is not a failure of natural law, but a reflection of limited familiarity. The Earth, in its full range, operates beyond the boundaries of everyday experience. These places expose that range. They demonstrate that reality is broader than expectation. And in doing so, they redefine what is considered normal, not by altering the planet itself, but by expanding the framework through which it is understood.